So we had a question yesterday about numbers 13 and 16. And I do have an answer. Both mathematical, this is Joel, right? Both mathematical and a conceptual idea as to why the answer to, what numbers were they again? 16. The answer to 16 is not just 1/2 of your answer to 13. First of all, I solved for the electric field for both of these in terms of the charge and the length of the actual rod that's been bent. And as you see, this guy is exactly, this guy, the half circle is exactly 4 times larger. The magnitude of the electric field is 4 times larger than the magnitude of the electric field of the quarter circle. The reason conceptually that it's not 1/2, that this guy isn't 1/2 of that guy, is because if you're going to make that assumption, you're assuming that the length of the rod is the same, right? The length of the rod is the same. So the total charge would be the same if we're just saying charge Q. But this rod right here, if this guy had the same length as this guy, then I would have to move it down, and then the radius would be 1/2 of the radius. And if you were to solve for the electric field in terms of radius, you'd see that you get the same result for both cases. But if we had the same length of rod, this guy's radius would be 1/2 of this guy's radius. And because radius gets squared in the equation, that 1/2 gets squared. And so you end up with 1/4. Right? And so that's just how it ends up working out. So to make that assumption would be to assume that the lengths of these two rods are the same. If the lengths were the same, this radius would be 1/2 of that radius. Right? Because I'd have to move this down so that I can form the half circle. But if you work it all out, like it looks exactly the same up till here in both problems. I did the whole solution just so you guys could see that. It looks exactly the same up to here. But then I'm not given the radius of the circle, I'm given the length, right? And if I'm given the length, then I make the substitution for length. In this case, it's just pi times r, but in this case, it's pi times r divided by 2. Because the radius the length is, the length of the rod here is pi times the radius. The length of the rod here is pi over 2 times the radius. Yeah. Yes?
Is the integral of cosine, I thought that was positive sign. I was thinking of the circle thing and it's fudge.
The integral of... Oh, it is! Oh my gosh. You get the same result though. Yeah. I was just seeing if anyone was paying attention. Good job. You passed for today. Everyone else failed. How embarrassing. Where's my black marker? Where's my black marker? Oh, you guys. Someone's stealing my stuff.
Absolutely. Send my stuff. I'm sorry.
Gross.
You can get it in like a few hours.
Even more gross. Okay, the magnitudes are the same. Yeah. Oh man, how embarrassing. How embarrassing. So does that clear that up? You good? Okay. That was a good question. That was perplexing me. I had to work out the whole thing for both of them and then think about it, looking at the equation, looking at this before. Oh, that's the explanation. Yeah, because that was throwing me off.
Aren't you so smart, Joel?
Yes, kudos to Joel for coming up with the best question yesterday. But shame on Joel for making me have to think. Okay. So now that we're professionals at calculating electric fields to extended charge distributions, let's start talking about how to do the same thing but a little more easily. Just like how you can determine areas under curved lines, curved graphs. more easily with an integral than you can with Riemann sums. Right? So just to show you, we calculated, due to a straight, a long thin rod, the electric field at a point. Right? If this is positive, then we have an electric field that points up that way. If this is a rod, insulating rod of uniform positive charge, we calculated that. That was the one that, let me just show you, that involved this much stuff. What is going on with my camera? That involved this much work. A lot of work to figure out the electric field at a point above the rod. And then very often, especially in circuits, these charged rods or wires, and wires are not insulating, but when they have charge flow through them, the charge density is pretty much the same everywhere. The electric fields, the important electric fields, are generally very close to the wires, and so we can consider them to be infinitely long. Well, if this rod then approached infinitely long, we took the limit as the length of the rod approached infinity and got an interesting result. That result, again, took a lot of work. It took a lot of work. It took us having to look up in a table of integrals because we literally can't do that integral at this point unless you know more calculus than I do. And what we'll see is that with Gauss's law, we can turn that 2-page problem into like 4 or 5 lines. Okay, Gauss's law simplifies a lot of this. Gauss's law will let us much more easily determine the electric field, a distance d above a sheet. As long as that sheet can be considered to be infinite in extent, we can do that with Gauss's law. And then what would be really difficult, really difficult, doing or by using techniques that we've used so far, say we have a uniformly charged insulating sphere that has charge uniformly distributed throughout its volume, and I want to know what the electric field is inside that sphere at a certain point. You can probably imagine that trying to do what we've been doing in the situations that we have, that would be very difficult to do, right? That would be a very difficult problem to solve, and I wouldn't even approach it without Gauss's law. Okay. So, we will then learn Gauss's law. There are two of the Maxwell's equations are called Gauss's laws. One is for electric fields, one is for magnetic fields. They all describe fields. All Maxwell's equations describe fields, electric and magnetic fields. Usually when we say Gauss's law, though, we're talking about the one for electric fields, because the one for magnetic fields is just the integral is equal to 0. And that just, it's not used quite as often mathematically as Gauss's law for electric fields, because that's not just equal to 0. Yes, sir?
So would we be able to, like, for a large charged sheet, would we be able to assume that to be infinity if it's just like a single electron, because it's so small compared to the sheet?
Well, it's got to be close. It's got to be close to the sheet. Like what determines, what makes the sheet approach like infinite extent is compared to the distance from the sheet that we're interested in the electric field strength. So it's just the distance, it's not the actual charge. Decent question. Not as good as Joel's yesterday, but decent. All right. So, all that being the case, let me read what I wrote on today's module because I forgot. All right. So, we're going to watch a video from the Science Asylum today to introduce Maxwell's equations.
Not Fullerton?
No, not Dan Fullerton. This was Science Asylum. Matt Fullerton. Matt Fullerton. Dan Fullerton is good for like actual AP Physics C content, right? Science Asylum, just if you're just interested in science, if you're interested in physics, astronomy, stuff like that, and you don't want to get into the nitty gritty, but you do want to see equations, because he does show a lot of the equations, but then he just doesn't really elaborate on them too much. So today we'll have a brief introduction to Maxwell's equations, courtesy of the Science Asylum. Then we'll dig deeper into the first one, Gauss's law for electric fields. So you'll watch the video. The video is titled Maxwell's Equations Visualized, and then in parentheses, divergence and curl. Realize that the divergence and the curl, parentheses, and also the gradient, you might have heard of that, are the main vector derivative operators that you'll learn about when you take multivariable calculus, which is your third semester of calculus in college. And the differential form, meaning the derivative forms of Maxwell's equations, can be written in terms of those operators. It's kind of weird. Gauss's law, as we'll see it, as we'll use it, the integral form is much easier. They're much easier to deal with than the differential form because the differential form involves the divergence and the curl, which are vector derivatives that are pretty complicated. Because especially when we get to magnetic fields, you can't deal with magnetic fields without dealing with three-dimensional space. And then time as the fourth dimension. So he's going to mention. I'm saying that because, okay, that said, we will not deal with them in this class, the curl and the divergence. We will be using the integral version of Maxwell's equations, which are actually easier to use for the types of problems that we'll be encountering. They do, though, the differential and the integral form of Maxwell's equations do talk about the same thing, the same phenomenon. And Mr. Science Asylum doesn't really get heavy with the math anyway. He'll show the equation. He'll show what the divergence and curl are. But he doesn't get into, he's more describing what Maxwell's equations actually do. So this video is actually a fantastic introduction to the fundamental equations and what they represent. And I cannot tell you enough, because when I was learning this stuff, the conceptual understanding always lagged behind the mathematical proficiency. I could solve the problems just because I had solved them before and I kind of knew what I was doing, but the understanding came later. And so it was very difficult for me. I had to work really hard. I feel like if you understand the basic conceptual ideas behind this, then learning how to do the math and apply the math actually becomes easier. Just so you know, the divergence, just so you know what you're going to see, the divergence, and this isn't the same divergence as the divergence of an infinite sum or something like that. The divergence is the upside down triangle. It's called the del operator. If you have a function of, say, a function of vector, or a function of x, y, and z, a three-dimensional function, and if you just put this guy in front of it, then it's called the gradient. It's just the three-dimensional derivative, and involves things called partial derivatives that you'll learn about when you get to college. The divergence is the dot product of that del operator and the function. So the function of, usually it's x, y, z, because we're talking three dimensions. And so the dot product of the del operator, by the way, is just, I don't want to get into it. It involves something called partial derivatives. But it essentially differentiates in the x direction, in the y direction, and the z direction, and then adds them together. That's essentially what the del operator does, kind of. So if you see something like this in the video, he's talking about the divergence. The curl is the cross product of the del operator and some vector function, which again in three-dimensional space tells you a value, some kind of value that's determined by a three-dimensional position. It doesn't have to be like that. It could be any type of and in fact, when you start, you'll just be dealing with two-dimensional space and stuff like that. But just so you know, when you see the divergence, it'll be del dot something. When you see the curl, it'll be del cross something. And you can write Maxwell's equations in terms of these two. Two of the Maxwell's equations are divergence equations. Two of the Maxwell's equations are curl equations. He'll describe what divergence and curl are. But when we deal with Maxwell's equations, we're going to do the integral version. They're not going to really describe, well, they describe the same thing. It's just harder to see with the integral versions, but they're much easier to deal with. But what you want to understand is the concept of the surfaces that it'll draw and the field lines. The field lines that are either going into a surface or coming out of a surface, and how they circulate about each other. But again, I just want to say this so you're not like, well, what is he talking about? What is the curl? What's the divergence? This class, we're not going to use it. You will when you get to college. When you get third semester calculus and you do calculus-based physics, like higher level stuff, you will deal with the curl and the divergence. And that's all third semester calculus, vector calculus. It's all about the gradient, the curl, the divergence, Green's theorem, Stokes' theorem, all this fun stuff. But anyway, without further ado, with that long-winded introduction, let's see. Oh, thank you.
Wait, that's a magnet, not
Yeah. He's going to go through all four of them. He's going to talk about all four of them. But just understand, see in this picture here, you got a bunch of lines. He's going to make the analogy between field lines and like the flow, velocity flow of like fluid. Field lines don't do that. Electric and magnetic field lines don't flow. But if you make that analogy, it makes it a lot easier to understand. So if you have like field lines pointing this way, then you can think of it as like a magnetic flow or a flow of magnetic fluid in that direction. It makes it a little easier to understand.
That thing that looked like, oh my gosh, I just found out the way to see the vectors.
Wait, what? Yeah.
Seems like a super quick video.
And then also, if you go to this guy's video, there's another video by 3 Blue 1 Brown that's a lot longer that kind of covers the same thing. That's really good as well. So if you go to, I think that one says divergence and curl in the title. So 3 Blue 1 Brown has a great video. I'm not going to show it. It's 15 minutes long. And I feel like this one's a little easier to just absorb. Okay, so here's Mr. Science Asylum.
Hey crazies, sometimes math is unavoidable. Without it, we miss out on important insights. So what if, instead of avoiding math, we try to visualize it? I want to give you a glimpse inside my head for a few minutes.
This guy's an astrophysicist, by the way.
This episode was made possible by generous supporters on Patreon.
He knows his physics.
So the math I want to help you visualize today is divergence and curl. But this isn't a math channel, it's a science channel. We need context. Fluid flow seems like an obvious choice, but those aren't always simple like this. Sometimes they're rather complicated. And if we're being honest, I don't really understand fluid mechanics as much as I'd like to. I'm trying to teach myself, but that takes time. So we'll reserve fluid animations like this for analogies only. Let's focus on something I happen to know a lot about, the electromagnetic field, which is actually a combination of two different fields. An electric field, shown in blue, and a magnetic field, shown in orange.
As we'll see in the later part of this class, magnetic fields are created by moving charges. Moving charges create magnetic fields. If you didn't have charges in motion, you wouldn't have magnetic fields. A bar magnet, the motion that creates that is what they call the quantum mechanical spin of an electron, of the electrons within the bar magnet. That's what creates the magnetic fields. So that's what he's talking about, why it's moving. Rewind it just a little bit.
And a magnetic field, shown in orange. We did a whole series on how we discovered those fields and what they do, but I didn't talk about divergence and curl at all, and I think that was a mistake. So it's time to fix it. We have two behaviors, divergence and curl, acting on two different fields, electric and magnetic. That means we need four equations. They look something like this, the Maxwell Heaviside equations, which most people just call Maxwell's equations. Don't get me started. But these constants are just there to make the units work out. They're not actually important for understanding the equations. So I'll just set them all equal to 1 and do what I want. Alright, as we go through these one at a time, we'll look at the equation first, and then we'll see what we can do about making it more visual. Let's start with this one, also known as Gauss's law. It says the divergence of the electric field at some point equals the charge density at that same point. In other words, the reason the electric field isn't just zero everywhere is because electric charge exists. But this law tells us something about the shape of the field, too. Say we draw an imaginary sphere around some region of space. The outer surface of that sphere has electric field arrows sticking in or out of it. Since that sphere is imaginary, we can make it any size we like. But to find the divergence, we need to make that sphere really small. Like, just a bit larger than the size of a single point kind of small. You're such a little adorable sphere. Yes, you are. Yes, you are. Anyway, the divergence of a field tells us how much that field points away from that tiny sphere. If the field points into the sphere as much as it points out, then the divergence is 0. Gauss's law tells us there's no charge in that point. If the field points more out of that sphere than in, the divergence is a positive number.
We call when field lines point into or out of a surface, the amount of field lines that go into or out of a surface, we call that flux. So if it's electric fields, we call that electric flux. If it's a magnetic field, we call that magnetic flux.
Gauss's law tells us there's positive charge at that point. If the field points more into the sphere than out, the divergence is a negative number.
That's why, I'll rewind a little bit. The reason I point that out is because the integral version of Maxwell's equations actually they describe the flux of electric field or magnetic field lines through a surface. Okay. The ones that we'll use.
Law tells us there's no charge at that point. If the field points more out of that sphere than in, the divergence is a positive number. Gauss's law tells us there's positive charge at that point. If the field points more into the sphere than out, the divergence is a negative number. Gauss's law tells us there's negative charge at that point. Electric charge is the reason the field looks like that. Of course, that's all very static and a little boring. If it helps, you can imagine this electric field is the velocity field for some fluid instead. That way it's easier to see the inward and outward directions at any particular place. But it's important to remember this is just a visual tool. Nothing is actually flowing in this picture. There's no electromagnetic fluid. It's not a thing. We can interpret the other divergence equation the same way. It says the divergence of the magnetic field at some point is always equal to 0. So unlike with electricity, there's no such thing as magnetic charge. In other words, there are no magnetic monopoles. Magnetic poles, like north and south, always come in pairs. Consider the magnetic field around this bar magnet. Using that same imaginary sphere, the divergence is how much the field points away. Since the divergence of the magnetic field is always 0, there is always just as much field pointed into the sphere as there is pointed out of it, no matter where we put that sphere. This becomes pretty obvious using the fluid analogy. Every streamline that goes into the sphere comes back out. That's all there is to divergence. The curl, on the other hand... Why does this keep happening? Curl is a different story. Your first instinct might be to imagine those closed fluid loops again. And that's certainly an example of a curl. But this flow has a curl too, without loops of any kind. That's because the curl isn't really about the field itself. It's about what the field might cause. In this fluid example, say we draw a tiny imaginary circle somewhere on the screen. Oh, come on, man! If we imagine some kind of paddle attached to that circle, the difference in flow between the top and bottom will cause it to spin. So even though the field itself doesn't circulate, the things inside it will. Now let's get back to electromagnetism. Faraday's law says the curl of the electric field at some point equals the negative change in the magnetic field at...
So he'll say that Ampere's law is the hardest one. From a differential perspective, that is true. For us, Faraday's law will be the most difficult one because we do a simplified version of Ampere's law anyway. Faraday's law is going to be like the culmination of this class. This is the law that actually dictates how we produce electrical energy using magnetism. So when he says that Ampere's law is the hardest one, that is true from a certain point of view. Yeah. So let's go.
Will cause it to spin, circulate, the things inside it will. Now let's get back to electromagnetism. Faraday's law says the curl of the electric field at some point equals the negative change in the magnetic field at that same point. Say we draw a tiny imaginary circle again, and we notice a magnetic field passing through that circle. If that field is changing over time, Faraday's law tells us there must be an electric field that curls around the imaginary circle. The curl of that electric field will be opposite the change in the magnetic field. But remember, the curl isn't about the shape of the field. It's about what the field might cause. If our imaginary circle happens to be a metal ring, we'll get a circulating current. That result is what matters. So where was I again? Divergence of the electric field, divergence of the magnetic field, curl of the electric field. All right, there's one equation left, the curl of the magnetic field. It's pretty obvious from the bar magnet example that the magnetic field curls. But let's take a look at Ampere's law and see what it actually says. A curl in the magnetic field at some point can happen for one of two reasons. An electric current passing through that point, or a changing electric field at that point. It's the longest of the four equations, which is why I saved it for last. Don't panic, we can handle this. Say we've got an electric current in a wire. If we draw our imaginary circle so electric current passes through it, Ampere's law says the magnetic field should curl around that circle. Now let's say somewhere along this wire, we've got a capacitor. It'll act like a gap in the circuit, which means no steady current, which means no field. Unless that current is alternating. Alternating current, or AC, opens up a lot of possibilities for us. Since the current in the wires is changing on either side of the capacitor, the electric field inside the capacitor is also changing. That changing electric field creates a curl in the magnetic field around our circle, just like the current does in a wire. This keeps the behavior of the magnetic field smooth across the entire picture. There's a curl in the magnetic field all along the circuit chain. So, what's the best way to visualize Maxwell's equations? Using tiny imaginary shapes and a little imaginary fluid. Divergence tells us how much a field points toward or away from a point in space. For electric fields, that's caused by charges. For magnetic fields, it's always zero, so we know magnetic poles always come in pairs. Curl tells us which way something inside the field might spin or circulate. In electrodynamics, that means we'll probably get some kind of electric current. Just remember, those shapes are imaginary, and that fluid isn't really there. They're just tools to help us visualize the math. So, what do you think? Should I do more videos like this? Please share your thoughts and comments. Also, maybe answer the poll that pops up over here somewhere. If you want to see the actual math of divergence and curl, there's a whole chapter.
See, there's the del operator. That's what it looks like. The gradient, if it's just the del operator operating on a function, then the gradient is the partial derivative of that function with respect to x plus the partial derivative of that function with respect to y plus the x hat, y hat, z hat. That could be I hat, j hat, k hat. But anyway, and then there's the divergence there. The curl is definitely a lot more complicated. You got a matrix. It's defined in terms of a matrix. The divergence is a little easier. But,
big news though, it's a physical book now. What?
He wrote that, by the way. You can buy it from him. It's pretty good. I haven't bought it, but I've read some of it.
No, right? It's crazy. It makes it feel so much more real to me. It's available through lulu.com, which helped to keep the price reasonable. Links for both the ebook version and the physical version can be found in the doobly-doo. Thanks for liking and sharing this video.
Anyway, if you've never seen a Science Slam, I've played him in here before, haven't I?
Yeah, no.
No? Well, it's good stuff.
Maybe last year, whenever I remember you did it.
Yeah, last year. You remember that.
It sounds like he was doing a bad impression of Ben Shapiro the whole time.
No, Ben Shapiro does a bad impression of Nick Lucid.
I thought Dan Fullerton sounded like Ben Shapiro.
Well, yeah.
Okay, that one I'll say. All right. Okay. Where's my remote? Okay. So, again, we don't deal with the divergence or the curl in this class. But we can get the same results. We can get the same results by talking about electric flux, which is a different way of describing the same phenomenon. The divergence, I feel like, is a little easy to understand, right? If it points out, we consider it to be positive. If it points in, it's negative. If you have a positive charge surrounded by an invisible sphere, then the field lines point out. So we call that positive flux. If you have a negative charge surrounded by an invisible sphere, imaginary sphere, the field lines all point into the sphere. And so we call that negative flux. If you have a positive charge here, a negative charge here, and then you got that invisible sphere here, well, the field lines are going to point from one towards the other. Every field line that goes into the sphere comes out. And so the net flux there is zero, because flux in is defined as negative, flux out is defined as positive. Okay. All right. So that's going to be the springboard. Again, 3 blue, 1 brown has a great video on the same topic, Maxwell's equations and fields and the curl and the divergence. And then his videos are definitely more geared towards people that might actually have to learn how to deal with that stuff. So I really recommend 3 blue, 1 brown. Great calculus playlist, great linear algebra playlist. So I'd recommend those. Anyway, so as I said in the beginning, Gauss's law, as we'll see and as we use it for situations involving pretty high degree of symmetry, it really simplifies a lot of results that we've painstakingly with brute force calculus had to derive thus far over the last week or so. But to use Gauss's law, we have to first, and again, when you just say Gauss's law, it's Gauss's law for electric fields. Gauss's law for magnetism really is, yes, you can mathematically deal with stuff with it, but in this class we're really not going to. It's just going to tell us that there's no magnetic monopoles. That means there's no imaginary sphere you can put within any magnetic field that will not have the same amount of field lines exiting as are entering. There's no way of doing it, even within the magnet itself. You put a little imaginary sphere within a magnet, the same number of field lines are going in and coming out. So like a charge, which you can enclose within an imaginary sphere, and have positive or negative field line, positive or negative flux. That can't happen with magnetic fields. So when we say Gauss's law, usually we're just talking about Gauss's law for electric fields. To understand the version of Gauss's law that we're going to deal with, we must talk about electric flux. Electric flux. And just what I have in my notes here makes it easier for me to understand. It is a term associated with a field that is bound by an area. I'm going to have a couple different ways of looking at what electric flux is, and then I'll show examples. I'll show some drawings that really should drive the point home. We can also think of it as the amount, and this is the main way that I think about flux. It's the amount of field lines. And remember, there's an infinite number of field lines, in quotes, that exist within space, right? But we can indicate the strength of the electric field by the number of field lines that we draw, right? We learned that from the quest assignment two quest assignments ago. So we can think of flux as being the amount of field lines or just the amount of electric field. So a stronger magnetic field has more flux than a weaker one. The amount of field lines passing through a surface. And in order to deal with electric flux, we need to define another quantity, another useful tool called an area vector. Area vector. It's literally what it means. It's a vector that represents an area. Okay, it's kind of strange, but let me just show you what I mean by that. Sorry, I should have written that up here. Area vector. So let's say we have a surface, and let's pretend it's like a plane that's oriented like this, but I'm going to offset a little bit so I can actually draw it on the board in a way that you can see it. So I have a plane, say at some angle like this. Not blue. My field lines are in blue. This.
Field lines are blue and yellow.
Yeah, that's the actual colored field lines. Surfaces are always green.
That's why we can't see them, because they're in the sky.
The most ancient figure.
Isn't flux something they use in welding?
What's that?
Is flux something they use in welding?
Yes, that's a different type of flux, yeah.
So you can see flux.
Yes, you can see that type of flux, yeah.
I mean,
If you're soldering, you use flux. That very different type of flux. Okay, so let's say I want to draw a vector that represents this area. Well, a vector, and this is a mathematical concept. This is a concept from mathematics that physicists then borrowed to do this. We can indicate the area of this vector by drawing a vector that is normal to its surface and have the length of that vector indicate the actual size of the area. Okay? So that would be an area vector. So A, in this case, our area vector is always normal to the surface. And yes, we've done normal forces for years now, but normal is a mathematical construct as well. A normal is just a ray that's drawn from a surface that is perpendicular to the surface at all points. Yeah.
Does that mean all other vectors are weird?
Yes. Yes. Abnormal vectors. Okay. And so the definition, using this area vector, and let's say that I have electric field lines that are going from this side to this side, they're actually going through, so let me draw it like this. It would be like an electric field line coming in and then coming out. Pretend I'm drawing this well. Those are my electric field lines. With this definition, with this with this mathematical definition of an area vector and electric fields, which we already know how to deal with, we can define electric flux, which gets the symbol capital Phi, which is like little phi, but with horizontal lines, with a subscript E, because we want to talk about electric flux here, not magnetic flux, which we'll talk about next decade sometime, I don't know.
Sometime.
Electric flux is simply the dot product of the electric field and the area vector. E dot A.
This is electric flux?
Electric flux. I should have said that, sorry. Electric flux is defined as the dot product of the electric field and the area vector. And that should make sense. Dot product is going to be EA times the cosine of the angle between them. The bigger the area, the more flux. The more field lines go through the surface, right? If I make this area bigger and I have a uniform field in the space, you get more. If I have a smaller area, I get smaller. If I have less electric field lines, I get smaller flux. If I have more electric field lines, meaning stronger electric field, I have more flux. Yeah.
Oh, that makes sense. It's going through.
What's that?
I said if it's going through like at an angle though too, like it makes
Yeah, and so that's where we're going now. So if I have that same situation, I have that same surface. Or you can also think of it as taking this surface and then rotating it, right? If I was to rotate it, the more parallel this plane gets to the electric field, the less electric field lines are actually going through the surface, right? Or I can think of that same area vector, but then, and to really drive this point home, let me actually draw two more electric field lines through this surface. If I then have an electric field with the same electric field density coming this way, sorry, I need to be consistent here. I'm not being consistent. I blame you.
mess me up.
How dare you?
Alright, so I have electric flux here. I think I've exaggerated it. But the electric flux through that surface is going to be small, right? And I feel like if you took it this way, if this is our area, and I have the electric field lines going through, and I start rotating it like this or like this, I get less electric field lines through it, right? And so I can describe that relationship by, that's why we have the dot product. It's not simply the product, it's the dot product, because really it's, and here, if I wanted to calculate the electric flux, it would be the electric field times the area times the cosine of the angle between them. Why the cosine? And what is the angle? Well, the angle is this angle right here. The angle between one of the electric field lines and the plane. So it's the same equation, but to actually compute it, we just do multiply the electric field strength, which we know how to calculate now, times the area that is represented by the magnitude of the vector, times the cosine of the angle that exists between them. Cool beans?
I really thought an area vector was just gonna be a really fat arrow.
Just
You could draw it that way. Say the fatter the arrow, the bigger the magnitude. I don't know. All right, y'all with me?
Yeah.
Okay. This is the key. With the differential form, the curl and divergence form, you don't really need to talk about flux, although it is associated. If we're using the integral form, which as you'll see makes our lives a lot easier for certain situations, then you got to understand what electric flux is. It's literally, just think of it as the amount of electric field lines going through a surface. The orientation of that surface does dictate how many field lines are going to be going through it. If you have a certain amount of field lines in a certain direction, the orientation of a surface within that space will dictate how many field lines actually get through.
Is there a certain specific direction the area vector must point, or could it technically point in the opposite direction, depending on how it is?
Yeah, if you have a two-dimensional surface in three-dimensional space, yeah, one side an area vector will point that way, the other side it'll point that way, and we'll deal with situations like that. Probably not today because we're running out of time, but probably Monday. Can I erase?
10th dimensional space.
No, never.
Yeah, 10-dimensional space will be 2 weeks from now.
Well, what that even mean? Like, is that something you could mathematically deal with? Or is it like,
I watched this video.
10-dimensional space?
Sixth grade.
Yeah.
That was like imagining, like being able to visualize the 10th dimension. It was weird.
Yeah, it's. I can't do it. But I've watched videos about it and I've listened to people talk about it. And no, if string theory is true, the most popular version of string theory predicts 10 spatial dimensions.
Isn't that like linear algebra?
Yeah. Well, you can deal with multi-dimensional space using linear algebra concepts, but those dimensions can represent physical quantities, right? And so it's not a stretch to the brain because you don't really need to see a surface in that many dimensions in order to make sense of what is being described. So if you want to talk about a volume, if you take a cube and then you just heat up one side of it at one point, the way that heat flows through the cube, like if you want to provide a differential equation that will describe that, it's going to be multidimensional. Because if you take a single rod and I put a lighter here, then that heat is going to start spreading through this guy. So the rate of heat flow is going to be a function of time. It's also going to be a function of the dimension of the rod. And so that I can plot that on 3-dimensional axes. But if I have a 3-dimensional volume, right, then I have 3 spatial dimensions, plus I need a time axis, plus I need a heat flow axis. I think that's how it works. Something like that. And so that would require a 5-dimensional graph, which you can't really conceptualize, but mathematically, if you know how to deal with the calculus, with the mathematics, you can do it. But yeah, their string theory predicts 10 literal spatial dimensions. Right? What that looks like, who knows? People smarter than I am.
You're just jumping in and out of timelines.
I live in the 9th one.
You live in the 9th one?
Yeah, I go home to it. I come here for...
They make analogies like an ant on a globe would consider that 2-dimensional object that exists in 3-dimensional space as 2-dimensional, right? And so you just go up one step, and that would be 4th dimension. Okay, let's go back to what I actually know about, though. So let's talk about what if our surface is curvy. It's a curvy surface. So that means that the angle between the electric field lines, and here we're assuming still constant electric field, a uniform electric field existing in the space, say maybe between capacitor plates. So I have a varying theta between the electric field and the area vectors. So I'll try to draw that by like doing something like this.
It's a flag.
So it's like this, right? You got me?
Yeah.
Make sure that's on video. It's like this. All right, and so obviously the area vectors are all going to be changing. The electric field, let's say the electric field lines are all horizontal. I'm just going to draw them through so it takes less time. But these electric field lines are passing through the surface. Okay. But the area vector, there is not one area vector that covers the entire area, right? It doesn't work like that. So the area vector, what I need to do is break this area up into an infinite number of infinitesimally small areas. And so I can say find this little area vector here that's on the part of that's right there, and then I can draw a little vector dA. Right? And so there is a little bit of like a little tiny differential infinitesimally small amount of electric field going through that infinitesimally small area. And with that, I can say, well, the infinitesimally small amount of electric flux going through that area is then the integral, not the integral, is the dot product of E and dA.
Okay.
And then if I want to determine the total flux through this sheet, I just integrate both sides. And so the integral of this is just going to give me the total electric flux. That's going to be the integral of E dot dA. In this class, we would not do this integral. because this is a two-dimensional object that's sitting in three-dimensional space, and there's not much symmetry here, and so this is actually a very difficult problem. Doing this integral is very difficult, because dA is like dx dy, right? That's a double integral. Have you ever seen stuff like this, right? And that's third semester calculus when you start dealing with that stuff. So when we take this to the next level with Gauss's law, we'll actually just deal with with situations in which we have a lot of symmetry, like a single charge surrounded by a sphere, or a spherical charge distribution. But with that, we can take, like I said, an insulating sphere that is charged uniformly and determine the electric field inside of it by using instead of using like these shapes that are not symmetric in the space within the space that they reside in. We use these very symmetrical shapes like spheres, cylinders, spheres and cylinders, really, what it boils down to determine electric fields much more quickly, much more easily. So the key is that electric flux is the underpinning of the integral version of Maxwell's equations, and so that's where we'll be going on Monday. Remember that quest assignment is due Sunday night. Any questions?
What's that symbol called?
What?
The one for Flux?
This one?
Yes.
Phi.
It's capital.
That's capital Phi.
I prefer fat I.
Fat what?
I.
Fat I? There you go. I like that. Fat I. Yeah.